Hi everyone, my name is Yuan Chen. I am a master's student at HCI Lab of the University of Waterloo, supervised by Keiko, Katsuragawa, and Edward Lank. Today, I will be presenting our paper Understanding Viewport and Word-Based Pointing with Everyday Smart Devices in Immersive Augmented Reality. Pointing and selecting are foundational aspects of interaction in physical and virtual world, and personal smart devices have frequently been used as input devices. Previous work has contrasted a set of different pointing techniques using phone and watch to support distant pointing with external displays. Our initial goal was to replicate these aspects in AR environments because in this environment, it is often the case that users must interact with distant projected content. However, a challenge presents itself on adapting different pointing techniques using smart devices to AR. While distant pointing is a common task within AR environments, techniques for pointing remain fragmented across head-mounted displays. The use of specialized controllers, specialized gestures, and various tracking technologies all contribute to this fragmentation. More broadly, the input techniques can be segmented into two metaphors for head-mounted display environments: the word-based metaphor and the viewport-based metaphor. The word-based pointing metaphor allows the cursor to move independently of the head-mounted display, while the viewport-based pointing metaphor places the cursor within the viewport of the head-mounted display and the cursor moves with the head movements. So, with these two pointing paradigms co-found, we want to answer three questions in this work. First, we want to know how these two pointing paradigms affect the selection performance in either AR or VR. Second, we want to explore how various pointing techniques and devices affect users' performance in AR. Last, by answering these two questions, we want to know how to design efficient pointing techniques using personal devices in the immersive environment. But before we go into details of our work, let's take a step back and look at some related work. Viewport and word-based pointing techniques have been widely used. With viewport-based pointing, users are aware of the cursor and can move it with head rotation, so researchers can design and evaluate multimodal techniques with head and gaze interaction. While in a word-based pointing paradigm, users can interact with objects even without looking at them. Phone and watch are also well explored in both physical and virtual environments as input devices. They can provide 6 degrees of freedom input for various interactions. Although many applications use viewport and word-based input paradigms, and explores personal device interactions in AR and VR, our work focuses on explicitly comparing different types of pointing techniques using phone and watch with these two pointing paradigms. Our methods consist of three parts: pointing paradigms, pointing techniques, and selection. The first pointing paradigm is viewport center, which is a commonly used solution for target selection in many existing head-mounted displays. In viewport center, the cursor is always located at the center of the viewport, and its movement corresponds to a user's head rotation. In the context of our viewport boundary, the boundary is a band around the edge of the display. When a user's head is stable, a cursor inside the display can be repositioned by manipulating an input device. When the head moves slightly, if the cursor is within the boundary but not pushed by the boundary, the cursor stays fixed in position. However, if the head moves sufficiently far that the boundary contacts the cursor is pushed in the direction of the head movement such that it still stays within the boundary. Word is a word-based paradigm. In the word condition, cursor movement is independent of head movement and only relies on input devices for control. For pointing techniques using personal devices, there are three types summarized in previous work The first type is relative touch-based techniques, where cursor movement is relative to the finger's movement on the touch screen. The second is absolute touch-based techniques, where we map a user's finger location on the touch screen to a consistent position of the virtual cursor on either the viewport or the virtual wall. The third is relative rotation-based techniques, where we implement a fixed origin ray casting and the origin of the ray is located at the camera of the head-mounted display. We implement these techniques using phone and watch. To select targets, users simply need to tap on the touchscreen, except for rotation-based techniques using smartwatch, where users need to rotate their wrist for selection. For a quick recall, we have 3 pointing paradigms, 5 pointing techniques, and 2 selection methods. We define pointing condition as the combination of pointing paradigms and pointing techniques, where viewport center plus tap is considered as the baseline in this study. To evaluate these pointing conditions, we designed the experiments as followed. We use fabricated walls to create a cubic room and generate 4 virtual walls. Participants are asked to point at the targets following the provided instructions. We separate our experiment into 2 studies, one with smartphone and one with smartwatch, and evaluate these pointing conditions in 4 dimensions. In study 1, viewport center is significantly faster than other pointing conditions. By refactoring pointing condition into pointing paradigm and pointing technique, we found significant effects of pointing paradigm and pointing technique on completion time. Pointing techniques with viewport boundary are all significantly faster than those with word-based metaphors. Absolute touch-based techniques are all significantly slower than relative touch-based and rotation-based pointing techniques. While viewport center is faster than other pointing conditions, it has much higher error rate and relatively high offset distance. Generally, pointing techniques with the word-based metaphor causes fewer errors and smaller offset distance than those with viewport-based metaphors. When looking at the NASA TLX, it shows that the viewport-based pointing conditions have lower task load than the word-based pointing conditions, and in fact that seems to hold regardless of the technique. When looking at the Fitts law, we notice that in the word perspective, when a target is generated outside the field of view, the continuous moving of the finger on the screen without lowering the position of the cursor will cause the cursor to exceed the target position multiple times, such that actual physical effort is needed to move the cursor back. Now, when we look at the user study 2, similar to study 1, viewport center is significantly faster than other pointing conditions. Viewport-based pointing conditions are faster than or almost equal to word-based pointing conditions. Again, considering both error rate and offset distance, the result is similar to that in study 1 with viewport center having the highest error rate but relatively low offset distance. The TRX result of study 2 shows a consistent result as what study 1 shows. Viewport-based pointing techniques have lower task load for all attributes than word-based pointing conditions using the same pointing technique. We observe a similar problem for touch relative input in word perspective for Fitts law. Because of the need to move the cursor for a long distance, participants will lose track of the cursor, overshoot, and need to perform costly corrections. So what can we learn from these results? A straightforward interpretation is as followed. First, viewport-based pointing techniques are faster, as accurate, and require less cognitive workload. Second, with the same pointing paradigm, relative touch-based techniques are faster, more accurate, and have lower task-cognitive load and offset distance. Third, relative rotation-based techniques have different performance across devices. Last, viewport center is faster, but has higher error rate and offset distance. To design efficient pointing conditions, we should consider the following aspects. First, regarding the viewport-based versus word-based pointing metaphor, viewport-based techniques improve selection speed without sacrificing accuracy. Second, users feel less fatigued mentally and physically using viewport-based techniques. Second, when choosing the pointing conditions, techniques, and device, viewport center is still the fastest technique among all conditions, but it causes more errors for general cases. In other words, hand control is better than head control in terms of accuracy. Relative touch-based techniques using phone and watch with viewport boundary are good alternatives if targets are on virtual surfaces. If targets are jetted into the air, rotation-based techniques using phone with viewport viewing is then a very good choice for control. We noticed that rotation-based techniques using smartwatches cause fewer errors and high offset distance, probably due to two reasons. First, we apply one-to-one mapping between device orientation and ray orientation. Second, we noticed that participants move their forearms more carefully and rotate their wrists more deliberately when they are selecting targets. In future work, we want to replicate this work in VR environments with specialized controllers. We also want to study more complicated AR environments, such as a living room with furniture or clouded classroom. We also want to explore capabilities of smart devices to achieve various tasks, such as proximal object selection and virtual joint manipulation. To conclude, in this paper, we explore various phone-based and watch-based pointing techniques for AR interaction. We found that, while equally accurate, viewport-based techniques provide faster and low-fatigue input. We also demonstrate that modern smart devices are effective input devices in AR environments. As these personal devices expand in sensing capabilities, they provide an exciting platform to support rich input in head-mounted display interactions. For more details, please look at our paper. Thank you.